Okay guys, welcome back. So in the last video I talked about a simple application of Boyle's law. So Boyle's law was important for systems in which the absolute temperature was kept constant and to understand the variation between the pressure and the volume, and also the mass is constant. Alright. So in the last video I talked about the Boyle's law, and in the previous videos I talked about Charles' law and the explanation of Gauss' laws and the graphs, right? And the graphs of gas laws. Gas laws means graphs of Boyle's law and Charles' law. So I have drawn all those and I have come here. Now what actually happened? Now in the theory of Boyle's law, what actually happened was that before going to this topic, for both Boyle's law and Charles' law, I kept the mass constant. So if the mass is constant, the number of moles for that gas, right? Number of moles for that gas is constant. So if the number of moles for that gas is constant, what actually happens is that the number of molecules or number of atoms will be constant. So what actually happens is that when the mass is constant, mass is used as a constraint, right? So mass is a constant, so mass should be a constant in order to put that law. So for what actually happened for the Boyle's law, was that I also kept the absolute temperature constant, right? And for the Charles law, I kept the pressure constant. Now what actually happens? What actually happens when all these three, the pressure, the volume and the absolute temperature changes? So for the Boyle's law, what actually happened was absolute temperature was kept constant. For the Charles law, the pressure was kept constant. Now what I'm going to do is that I'm going to take all those and change all those, right? Change all those three, right? The pressure, the volume and the absolute temperature. But here also I'll keep the mass constant. What I mean by keeping the mass constant is that I'm keeping the number of moles for this gas equals to 1, right? So the number of moles will be 1. So it's a unit mole gas, right? Unit mole gas I'm using. So in order to understand what I'm going to do here, right, I'll take a simple separate apparatus like this, right? Simple apparatus like this. So what I'm going to do here is that now I have three systems. What I mean by systems is that these are closed apparatus or closed vessels. So this is a vessel, this is another vessel, this is another vessel. I'll take all these vessels to be identical, right? All these three vessels are identical, and I'll use a piston to change the pressure and change the volume. By increasing the pressure, I can't say I'm increasing the volume as well because the temperature is changing. So I can change the pressure, I can change the volume, and externally I can change the temperature, so the absolute temperature as well. Alright. So if I take this system, now for this system, what actually happens is that now I'll take this to be the first system, this to be the second system, right, and this to be the third system, right. For the first and the second systems, these two systems, this one and this one, what actually happens is that the pressure is a constant, right? The pressure is a constant. So if the pressure is a constant, I can easily put Charles' law in order to find the final volume of this gas at the second instance, so for the second apparatus. So from Charles' law, I can say from Charles' law, you can say V1 by T1 is equal to V by T2. Now assume that T1 and T2 are both absolute temperatures. So I have not taken the time the T2 is greater than T1. So T2 will be any value, T1 will be any value, and so I can say whether the volume is increasing or decreasing. I will not use that constraint, right? I will not use that constraint whether it's increasing or decreasing. I'll just say it's changing, right? So it's simple to understand. So for the second system, what actually happens is that now the temperature is a constant for the second and third systems. For the second and third systems, the temperature is a constant. So what I can do is that for the second, now this is for the first and second systems. For the first and second systems I put Charles' law. For the first and second systems I put Charles' law, and I got an equation like this. I'll take it to be equation number 1. For the second and third system, what I'm going to say is, since the temperature is a constant, temperature is a constant, is used as a constant, so I can put Boyle's law. So from Boyle's law, so from Boyle's law I can say P1 times V is equal to P1 times V, right? P1 is the pressure here, V is the volume here, is equal to the pressure here P2 times its volume at that point, which is V2. So P2 times V2, right? So I'll take this to be equation number 2. So from equation 1 I can easily get now, assume that this V has not been given for this system, I just took an arbitrary value, right? Assume that V has not been given, I just took an arbitrary value in order to apply the equations like this. So what I can say is from equation 1 I can I can take the value of V and then substitute the value of V here and find another equation. So from equation 1 I can say, from equation 1, so I can cross multiply here, so that V1 times T2 divided by T1 is equal to V, right? Cross multiply here and divide it by T1, right? So I can isolate V, so V is equal to V1 times T2 divided by T1. V1 times T2 divided by T1. So I'll take this to be equation 3, right? Equation 3. So from 3 I can substitute the value of V to 2, from 3 to 2, right? From 3 to 2, so what actually happens is that P1 times, from equation 2, V we have found in equation 3, that's the value I am going to substitute here. This is V1 by V1 times T2, divided by T1 is equal to P2 times V2. So that's the equation that I am getting. So assuming that the temperature is not zero, normally we cannot reach an absolute zero temperature. Absolute zero temperature is just a concept, yes, used as a concept. Normally, although we achieve 0 Celsius or 0 Fahrenheit temperature, we cannot easily achieve an absolute zero temperature, right? Absolute zero temperature means minus 273 degrees of Celsius. So that's just a concept, like the concept of infinity. We have never reached there. So the absolute temperature of zero absolute temperature is also like that. So what I mean is 0 Kelvin is completely unreachable. So T2 cannot be 0. So I can divide T2. I can divide both sides by T2. So if I divide this side by T2, that T2 to dividing T2 will cancel, and dividing this side by T2 will remain, and I can isolate this term and another term here. So T2 divided by T2 is T1. So P1 times V1 divided by T1 will be remaining in this part, or the left hand side of this equation. So that will be equal to P2 times V2, and that's divided by T2. Right. So this is another important relationship. Now what actually happens is that there is some pressure here, there is some pressure in the left hand side, pressure times the volume divided by some temperature. So that is in the left hand side, and that is the same thing that you get in the right hand side as well. So what actually happens is what actually has happened is that the pressure has changed to some value, the volume has changed to some value, and the absolute temperature has changed to some value. But what actually happens is that there is some pressure multiplied by some volume of a gas divided or taking a quotient of some absolute temperature. So what actually happens is that you know that from Boyle's law and Charles' law, if P1 V1 equals P2 V2, I told you that PV is K from the converse theory of Boyle's law. From Charles' law, if V1 by T1 is equal to V2 by T2, from the converse theory of Charles' law, I explained to you that if you get such an equation, V1 by V by T is a constant. So if you get the same quotient like this, on both sides, what actually happens is that for any temperature, for any pressure, and for any volume, PV by T should be a constant, right? Not is a constant, should be a constant. So what is the constraint of happening? What is the constraint of happening is that the number of moles should be 1, or number of moles, I'll take it to be 1, but you can also say the number of moles is constant, right? So if the number of moles is constant, P times V by T is a constant. So P times V by T is normally called the combined gas law, because now this is the first equation I got is the equation I got from Charles' law. The second equation I got is from the Boyle's law. So what I'm doing is that I got the third equation by isolating the arbitrary value of V I got to solve these equations, and then substituting the value of V here, and then solving it to make PV by T is a constant. So what I'm actually doing is that when I'm substituting, now this is the most important step in this derivation. This is the most important step in this derivation. What I'm doing is that when I'm substituting the value of V here, right? Substituting the value of V here, right? What I'm doing, this is from Charles' law, and I'm substituting it into Boyle's law. So what I'm doing is that I am joining these two laws. So it's a combination of these two laws. So this is popularly called the combined gas law. So combined gas law is very important in the concepts of gas laws, in that all the temperature, pressure and volume, all those changes. So it's another gas law. So in the next video I'll be explaining with you some examples in which the combined gas laws is of utmost importance when you are solving gas laws equations. And thanks for watching this video, and see you then.